Welcome! In this 7th lecture we cover the foundations of mathematics. In this part A we learn about sets. What is set theory? It's the foundation of mathematics, a language to describe all objects in mathematics, and also a tool to understand infinity. There are 4 parts in this lecture. In this first unit we look at the Boolean algebra of sets, then the second part we'll study infinity, then paradoxa, and finally the incompleteness theorem. A set is just a collection of objects. For example, we can take a universe of 27 cards in the game set. So there are 27 cards, and we can now form subsets. For example, the set of all red cards or the set of all cards with 2 objects in it. The intersection of these 2 sets has now 3 elements. You can also look at the union of all red or all oval shapes. This gives a set of 15 cards. A set is usually described by some properties. So in this case, there's shape, there's color, and there is number. So the surprise is that this universe produces an algebra similar as the numbers. It is called the Boolean ring, named after George Boole, who lived from 1815 to 1864. This is a nice documentary about the genius of George Boole. Operations and relations between sets can be illustrated with Venn diagrams. We can form intersection, union, or differences of sets. John Venn invented this picture, and it allows to illustrate sets and properties. And we have a ring. We have an addition and we have a multiplication. The addition is the symmetric difference, and the multiplication is the intersection. So all the rules we know from numbers holds, and you work on this in the homework. We have commutativity of multiplication and addition. We have a 0 element, the empty set, and we have the whole universe as the 1 element. We have associativity, distributivity, all the rules we know, we are familiar with. And here is an example which illustrates this. We can, for example, compute a plus b squared. So that's a plus b times a plus b, and we can FOIL out like in algebra. So this is a squared plus ab plus ba plus b squared, and now ab plus ba, that's plus ab by commutativity, and so it's 2 times ab. But there's a general rule in this Boolean algebra which is a little bit strange, that a plus a is always 0. So any set plus itself is 0. So ab plus ba is 0. So we just end up with a times a plus b times b. But there's another rule which says a times a is equal to a, because the intersection of the same set is itself. So in this case we have just proven with this computation that a plus b times a plus b is a plus b, which is a general property. Anyway, any set a times a is equal to a. So it's also relevant, this whole Boolean algebra is relevant in logic, where you do the addition is the exclusive OR, and the intersection is the AND. So this is quite universal.
Let me break this down for you. This sex scandal, or this supposed sex scandal, can all be explained with a Venn diagram. Remember,
this context, it's also interesting. Pedagogically, this set theory has been introduced in the very early curriculum in the 70s. And so there was, in the 70s, there was this first revolution, which was called the new math. And that's the abstraction of sets was introduced. And then there was a new math revolution in 1990, around where computer algebra systems, for example, were used more and more. And now we live in another revolution. It's already kind of almost over, but it's attack of the MOOCs, of the massive online open courses. About the new math, I mean, when this came, there was a game which kind of illustrates this well. It's a 114-page manual of a set game. It's a very complicated game. I don't understand it. Here are some pages. So not everybody liked the new math. So here is a critic from Richard Feynman. Also the math wars, this was in the 90s. Everything was done with computers. I have taught classes where every student was sitting in front of a computer. This was the math wars. It was actually triggered by the NCTM standards in 1989. And then the attack of the MOOCs, that's kind of what has happened recently. So these revolutions were for generation X, for generation Y, and generation Z. This is the end of part A. In this part B, we look at the concept of infinity. What is infinity? We need a guide.
Infinity, and beyond, and beyond.
And our guide is not Buzz Lightyear, but Georg Cantor, who lived from 1845 to 1918. So here's a clip from the Story of Math.
Cantor was one of my big heroes, actually. I think if I had to choose some theorems that I wish I'd proved, I think the couple that Cantor proved would be up there in my top 10.
And this is because, before Cantor, no one had really understood infinity. It was a tricky, slippery concept that didn't really seem to go anywhere. But Cantor showed that infinity could be perfectly understandable. Indeed, there wasn't just one infinity, but infinitely many infinities.
In order to understand infinity, we need to understand maps. The injectivity of maps and bijectivity of maps. A map is bijective if it is one-to-one, if every object in one set corresponds to exactly one object in the other set. It is called injective if just two different points are mapped into two different points on the other side. So injectivity is very important because it allows us to say when the cardinality of one set is smaller than the cardinality of B. That's what Cantor meant with being smaller. It means that there is an injective map which maps A to B. For example, the set of primes is smaller than the set of integers because the set of primes is a subset, so we can map every P to the integer P. That's an injective map. It's not surjective because not every element is reached, but it tells that the number of primes is smaller. We can also show that the number of primes is bigger, so one can find a map from the integers to the primes. N goes to the nth prime, and also this is injective, and so these two sets are equivalent. Cantor calls this cardinality is the same. So here's another example. So we have the natural numbers and we have the integers. Of course, the natural numbers is a subset of the integers, so there are less natural numbers than integers. So there's an injective map from the natural numbers to the integers. N just goes to n, and the injective, two different elements are going to two different elements. But then we can also show that the integers are actually equivalent. So we can enumerate the integers with natural numbers, and here's an explicit map. So we define f2n is equal to n, and f2n plus 1 is minus n. This is a Hilbert Hotel idea that we have not enough rooms, so we actually move every guest from room n to the room 2n, so we have space for more guests, and the more guests are the negative numbers here. So we have another map which is injective, and so actually this is a bijection. Even this map is a bijection between the integers, between the natural numbers and the integers. They are equivalent. The cardinality is the same type of infinity. In order to show that the rationals are equivalent, one needs a little bit more work. One idea is to put the rational numbers in the plane where it makes sense, and then go with a Ulam spiral through and enumerate everything. A little bit simpler is here just if you enumerate only the positive fractions, so you start with everything which is fractions of 2, fractions of 3, fractions of 4, etc. And here we enumerate all the fractions between 0 and 1. And also this can be clearly enumerated. You snake through the whole thing. First go to the first row, second row, third row.
Now imagine a line snaking back and forward diagonally through the fractions. By pulling this line straight, we can match up every fraction with one of the whole numbers. This means the fractions are the same sort of infinity as the whole numbers.
When we count the real numbers, that's a question which Cantor pondered and could answer. The surprise is actually that it's not possible. So it's a different type of infinities, and Cantor's proof is just genius. He assumes that we could enumerate all the reals, so we write them down. All this number 1 is here in this case 0.3528. Second number is 0.717. So we assume we can enumerate all these numbers in some way. And then he forms a new number, which is the diagonal, a diagonal formed from the diagonal, which we see here. So in the diagonal we see 0.75135, but he just adds 1 to each of the digits, and we get 0.86246. And so this new number is not part of the list, right? It cannot be the first number because it is different in the first digit. First number 8 doesn't match 7. Second digit also, third digit, all the digits are different. This number 0.86246 is not in the list of this enumeration. So that's the Cantor diagonal argument. As an application, Cantor proves a theorem that there exist transcendental numbers. So a number is called transcendental if it's not algebraic, and an algebraic number is a root of a polynomial with integer coefficients. So we can enumerate all these algebraic numbers. So this has the infinity of the integers, but then the real numbers there are much more real numbers. So most of the real numbers are actually transcendentals. So this is a great idea of Cantor and justifies the whole formalism. And then he went on and asked, is there infinity between the infinity of the natural numbers and the infinity of the reals? And Cantor could not answer that, and it became Hilbert's first problem at the turn of the century. But he created a beautiful universe of ordinals and cardinals. So the ordinals are just, the numbers we know, and then you can, Cantor starts to build the first transfinite number, which is omega, called omega, which is which is not finite, and then you can continue counting. We have omega plus 1, omega plus 2, omega times omega, omega square, omega cubed, omega to the omega, etc. So there's a whole universe of new numbers. And then there's also the cardinality. The cardinality is that we have the infinity of the integers, and then we have the infinity of the least upper bound of all countable cardinals. That's called Aleph 1, Aleph 0, Aleph 1. And the question is now, what is the cardinality of the reals? Is this Aleph 1? And that's the problem which we come to next. In this part C, we look at some vexing paradoxa. Questions like, what is mathematical truth? Are there consistent theories, or is there even a complete theory of all mathematics? One thinker who thought about this is Ludwig Wittgenstein. He's known for catchy slogans like, whereof one cannot speak, thereof one must be silent. Already the Greeks pondered fundamental questions. One of the puzzles is the liar's paradox. It is attributed to Epimenides, who lived around 600 BC. So here's the original statement. Epimenides, a Cretan, reportedly stated, the Cretans are always liars. The question, of course, is now, is this statement true or false? And in both cases you get into trouble. There are many variants of this. Here is one from the book of Gödel Escherbach by Douglas Hofstadter. It says, this sentence is false. The sentence shoots itself in the head, so it's a reference to itself on various levels. It's a highly recommended book. Hofstadter also formulated a law. His law is it always takes longer than you expect, even if you take into account Hofstadter's law. Therefore, work on the project. So here's another paradox due to Bertrand Russell. That's more serious. And so look at the set of X of all sets which do not contain themselves. The question is now, is X in the set X or not? So if X is in the set X, then by definition it's not in the set X. So if X is not in the set X, by definition it is in the set X. So it's kind of this liar paradox, but now framed in in a framework of set theory. Variants, like on this cup. Appears also in the movies. Here from Shrek 3. Surprise exams. Are there surprise exams? There's a theorem. There's no surprise exams. So if assume, for example, we wanted to make a surprise exam in this course until December 3rd, and December 3rd is out since the night before, you would know that there is tomorrow the exam has to happen, so you could prepare for it. So December 3rd is out, but then December 2nd is out because the night before you wouldn't have to know it has to be tomorrow, because if it's not tomorrow it would be the day after where you could prepare for it. So it's also December 2nd is out. Then like that you continue, December 1 is out, etc. I hope you don't feel dizzy. But all this self-reference is kind of a typical source for paradoxa. There's also a heap paradox. Taking a leaf away from a heap is still a heap. So this is not the end. In this last part, we look at some consequences of the theory which Cantor has founded. The question of whether there are consistent theories of mathematics. It was Zermelo and Frenkel who built a system in which the Russell paradox does not appear anymore. So here is this formal system of all mathematics called ZFZ. It has some very obvious statements like if two sets have the same elements, they are the same. Well, then there is this infinity axiom, there exists an infinite set, and so on. Hilbert's program is to call for an axiomatization of all mathematics together with a consistency proof. It's now called Hilbert's dream, and one of the attempts to realize this dream was Principia Mathematica by Bertrand Russell and Alfred North Whitehead. It's a huge opus, but this dream died. So it was Kurt Gödel who killed it and established that the Hilbert program is really just a dream. He proved two theorems. The first completeness theorem tells that in a strong enough theory, there are statements which cannot be proven within the theory. So what it means is you can build a statement A, which you can include in the theory, and you get a consistent extension, or you can take the opposite. You can assume not A and absorb it to the theory and get, again, a consistent extension. Another part, the second incompleteness theorem, tells that in any theory, the consistency of the theory cannot be proven within the theory. So one needs a larger theory than ZFC, for example, to prove that ZFC is consistent. So one has to leave the system. And Gödel had this idea of Gödel numbering. Gödel did establish that one can talk about mathematical sentences like about numbers. Actually, one can just enumerate the sentences and so have them as part of the universe, the theory. The numbering is a bit like in this joke where prisoners tell jokes to each other by calling out numbers. One of the new prisoners tries it himself and shouts 63. Nobody laughs. Later somebody explains him that not only the joke itself, but also the way how the joke is told matters. You can use the Gödel numbering also for practical things like produce programs which print out themselves. Gödel is an interesting figure. Here's some gossip about him. In the end, because of obsessive fear of being poisoned, he starved himself to death. But he was a good friend of Einstein.
Every morning, Kurt Gödel, dressed in a white linen suit and wearing a fedora, would walk from his home along Mercer Street to the Institute. On his way, he would stop here at number 112 to pick up his closest friend, another European exile, Albert Einstein.
Many people have said Kurt Gödel is right up there with Aristotle, and that the incompleteness results were the first major results in logic since Aristotle.
So here's some literature. This is the end.